So let's see what are the chemical properties of compounds having this carbonyl group. The most important one is nucleophilic addition reaction. Most of the reactions in these aldehydes or ketones shows nucleophilic addition only. So let's see what is the nucleophilic addition. What is a nucleophile? Say Nu is a nucleophile with this negative charge. This nucleophile always searches for positive to form a bond. Okay, this is a nucleophile. It requires positive one to form a bond. So what is our carbonyl compound? C double bond O. Whether maybe aldehyde or ketone, this is our functional group. So in this functional group, what is going on? This oxygen is more electronegative than this carbon. So it attracts the electrons towards itself and leaving with a partial negative charge. And this carbon is having partial positive charge. So whenever a nucleophile comes here, it obviously attracts the carbon which is having the positive charge. So this is the simplest form of this nucleophilic addition. So nucleophile is going and adding at this carbon atom. So this is known as nucleophilic addition. So let's see what is the mechanism inside this one. It may be of two types. Not necessarily only nucleophile will come and attack. Even electrophile is also comes into our scene and attacks this carbonyl group. But the majority of the reaction goes by using nucleophile. But let's see with this electrophile also. So what is our carbonyl group, functional group? C double bond O. When a electrophile comes here, what is going to happen here? This electrophile requires electrons. This needs electrons. So here, what is going to give the electrons to this electrophile? This oxygen. From oxygen, this electrophile takes the electron, leaving the product as this one. This is the major product. So this electrophile takes the electron from this oxygen atom and converts this oxygen atom into +1. But if this oxygen atom is in this O+ state, it requires more electrons. So what is the next step? This oxygen atom attracts the electrons from this pi bond and leaving the carbon as C+, and it attains its own electrons. Now nucleophile will come and attack this carbon. So in this case also, nucleophile will come and attack the positive carbon atom, and electrophile will attach to the oxygen, partially negative oxygen atom. In this case also, the product is same, but not directly, but through electrophile attack first, next by the attack of nucleophile. In this type also, addition will occur, but this is a minor product when compared to nucleophilic addition. Electrophilic addition is a minor one. So let's see what is a nucleophilic addition. Actual nucleophile attack, let's see. This is type 2 if you say. If any nucleophile will come, it directly attacks the carbon. So what is going to happen here? As oxygen is more electronegative, it attracts the electrons towards itself, leaving the carbon as C positive, and then nucleophile comes here and attacks the carbon. So this negative charge on oxygen is balanced by the electrophile. So the product in these two types will be the same, but first one through the attack of electrophile and the second one through the attack of direct attack of nucleophile. So possibility is more in this type compared to the earlier one. So let's see what are the factors affecting the reactivity. So how can we decide which one is a greater reactive nature? Anyway, ketone is also having C double bond O, and our aldehyde is also having same functional group. So among those two, how can we say which one is more reactive? So for that, get to know which one is a greater reactive one, two factors will come here. One is steric factor, or else we can say this one as steric hindrance. This is the first factor, steric factor or steric hindrance. What is this steric hindrance? So if we consider any aldehyde, this is our aldehyde. If you take any ketone, this is our ketone. In this aldehyde, only one alkyl group is present, whereas in this ketone, two alkyl groups are present, whether it may be same or different, but two alkyl groups are present. But whereas in this aldehyde, only one alkyl group is present. So what the role is going to play whenever a nucleophile comes to attack or attach or add to this carbon plus atom, this alkyl group avoids the addition. It tries to avoid the addition of this nucleophile. But that repulsion is less in case of aldehyde, whereas in this ketone, the repulsion is more because two alkyl groups are present here. They are not at all letting the nucleophile come and attack the C positive, partially positive charged carbon atoms. So if at all bulky groups, alkyl groups, if alkyl groups increases, the reactive nature is decreases, we can say. So basing on this factor, aldehydes, we can say aldehydes are more reactive than ketones. So now let's see this one. Here I'm comparing two aldehydes. So among these two aldehydes, which is more reactive, a formaldehyde or acetaldehyde? Same thing, same formula applies here also. Steric hindrance is less here. So repulsion is less in this case as only hydrogens are present on both sides of the carbon atom. So it easily allows the nucleophile comes and adds to the carbon atom. In this case also okay, but somewhat less when compared to this compound. Then what about this one? This is our ketone. So same formula here, two methyl groups are there. So bulky groups are there. They are not at all going to allow the nucleophile to come and add to the carbon atom. So we can say that formaldehyde is more reactive when compared to acetaldehyde. This is more reactive when compared to our ketone or acetone. So what we going to learn from this? If at all any bulky groups are present, means carbon chain is increases, the reactive nature is decreases. So when we compare this sort of a thing, aromatic ring, this is much more less reactive when compared to our acetaldehyde. Why? Because here methyl group is there, but here one aryl group is there. So it further stops the nucleophile come and attack this carbon positive atom. So what we learned from this? If at all groups are increased, bulky groups are increased, or carbon chain is increased, the reactive nature is decreases. This is steric hindrance. Next one is, so from this, aldehydes are more reactive when compared to ketones. So the next factor is polar factor. So what is this polar factor and how it affects the reactivity of aldehydes and ketones? Let's see. So let's take the same example. Same example I am taking formaldehyde, acetaldehyde and ketone. So what is polar effect? How effectively the positive charge on carbon will it get, and how effectively the negative charge this oxygen will get comes into consideration here. So how it happens? As oxygen is more electronegative, it attracts the electrons towards itself, attaining more partial negative charge, so that carbon will get the partial positive charge. Same in this case also. So same in this case also. So here, in all these cases, carbon is having partial positive charge. So carbon requires electrons. But in this case, in this first case, no one is there to give electrons to this carbon. But in this case, this methyl group somewhat tries to give the electrons to this carbon by plus I effect. In this case, 2 CH3 groups tries to give the electron to the positive carbon atom, again by plus I effect. So in this case, in this formaldehyde case, this the electrons are obtained by nucleophile very easily. Whereas in this case, already electrons are given by this methyl group, and it is not at all going to allow the nucleophile to come and add to this one. And in this case also, because here in the group itself, the two bulky methyl groups are giving electrons to the carbon atom. So no need of getting electrons from the nucleophile. So based on this thing, the attack of the nucleophile will also decreases. Same as the above also, based on the polar factor also, this formaldehyde is more effective than this acetaldehyde compared to this ketone. So based on these two things, what we can say, aldehydes are more reactive when compared to ketones, based on the steric hindrance and as well as the polar factor also.